This one. This one. So, today I want to introduce another class of functions, these ones the so-called logarithmic functions. And they're related to exponentials in like an important way. So let's start with just this reminder. The graph of 2 to the x, what does it look like? Describe to me its properties. So for like extremely negative values, it's close to 0. If we were to extend this axis out, the y values of 2 to the x are basically 0. It has a y-intercept. Where is its y-intercept? 2 to the 0 is 1. Yeah. So the y-intercept is at 0, 1. And then it should like roughly keep doubling every unit interval. In fact, it'll exactly do that, but the graph is going to be a fast graph. So there's the graph of 2 to the x. Maybe I'll do some erasing so it passes the vertical line test. Take a look at that function. Does it pass the horizontal line test? So what extra adjective could you use to describe this function? One-to-one. Or injective if you like the fancier sounding one. Injective functions, one-to-one functions, have inverses. This has an inverse function. Let's talk about the inverse function. How does the graph of an inverse function compare with the original graph? How do you graph inverse functions? Switch the x and y values. Let's do that to this. So I see this point here at 0, 1. Where will it go on the graph of the inverse? 1, 0. I see this point here at like, if you plug in x equals 1, you get y equals 2, because 2 to the 1 is 2. So there's a point on that graph. What point do you therefore know is on the inverse? 2, 1. Now let's maybe do one more. 2 to the 2 is 4. 2, 4. There's a point on the graph of that function. So what graph is on the inverse? 4, 2. Maybe I'll try to get that scale right, because there's like a thing we're going to notice. Nice. And let's also pay attention to these values. So I see x values that are extremely negative, y values close to 0. So, labeling that. X equals negative and big paired with a y value that is close to 0 and positive. So there's a point on the graph of the original function. So that means that a point with x value very close to 0, y value very big and negative should be on the graph of the inverse function. So a point like down here. Nice. So what does the graph of the inverse function look like? Something like that. Cool. That's the type of function we're going to start studying now. There's the graph of the inverse function to 2 to the x. And I'll make up a name for it. We will call that the logarithm with base 2 of x. There's the new type of function we're going to be studying. These so-called logarithmic functions. And what they are in their heritage is inverse functions to exponential functions. And in some sense, that means that it's automatically going to be a little bit dicey to get a hold of these. Really understand what they're doing. In the same way that like root functions are hard to get a direct hold of. They're at their heart an inverse to something. In order to think about logs, you kind of need to think about undoing exponentials. But now that we have a name for this, we can like start doing stuff with it. So let's talk about conventions a little bit. The
The logarithmic function with base b, written log base b of x, is just the inverse function to b to the x, for any base. I guess the base had better be positive. You don't talk about -5 to the x at all, because you can't make sense of -5 to the 1/2. -5 to like the pi is even harder to understand. So we just won't. The book will say log of x when it means log base 10. And that's not an uncommon convention to use, that log just means log base 10. But that's not a universal convention. The natural logarithm is the logarithm with Euler's base, for the same reason as the natural exponential is the exponential with base e. It has really nice properties from the point of view of calculus. Logarithm has really nice properties from the point of view of calculus. Log base e does. It's given to that name for properties coming from calculus. Good. So, depending on what sort of system you're using, which base is the base that you assume if you don't indicate a base will differ. A lot of them will assume that log means log base 10. Probably your calculator, if you have to compute log of 5, will assume log base 10. But some of them will assume you mean log base e. And I don't know, let's just see a show of hands for what fields people are going into. Anyone going into like one of the hard sciences, physics, biology, chemistry, one of those? Yeah, cool. Your natural base is probably base 10. And the only thing that's natural about that base is you have 10 fingers. That's the only reason that we use base 10. And people are going into a computer science-y type field. Cool. For you, the natural base is probably base 2 because computer scientists have only 2 fingers. It's a good joke. If you're going into a field more closely related to mathematics, most natural base is going to be base e, and that's because of really nice properties coming from calculus. But different problems are appropriate for different bases, as we'll see as we progress. So let's think about inverse functions, what they mean. So if someone says y equals log base b, let's think about what that means. And I'm going to have this on the board because I'm going to reference it a lot. So there's an inverse function, right? Inverse functions have the job that they've like swapped the role of inputs and outputs. So when someone says y equals log base b of x, what they really mean is x. The thing that's the input on that side becomes the output on the other side, equals b, still a base, but now it's an exponent, to the y. You can translate between logarithms and exponents, and we'll see that this is really powerful. So let's just see some examples. If someone says 4 is equal to the log base 3 of 81, what that means is that 3 to the power of 4 equals 81. And just do a quick check. Is 3 to the 4 equal to 81? Nice. That means 4 is, in fact, the log base 3 of 81. So there's a logarithm you can compute. If someone says -1 is equal to the log base 7 of 1 over 7, what that means is the base 7 raised to the power -1 is equal to the thing inside of the log, 1 over 7. And again, let's just ask ourselves, is 7 to the -1 equal to 1 over 7? Yeah, that's what raising to the -1 means. So, log base 7 of 1 over 7 is in fact -1. Do this bit of translation. 3 is equal to the log base 5 of 125. What is that as an exponential equation? Yeah, that one. Excellent. 5, the base, raised to the power 3, equals 125. Groovy. And let's go the other way too. 2 to the power 10 equals 1024. What is that as a logarithmic equation? Yeah.
Log with the base of 2 equals 10.
Log base 2 of 1024 is equal to 10. Cool. That feel pretty good? So maybe we're noticing a few things, like 2 to the 10 is like pretty big. Like exponentials grow fast, we saw that. The log base 2 of 1,000 is like a pretty big number, is 10. Logarithms grow, but they grow kind of slowly. And let's just, there will be some observations we'll make at the end of this, but let's think about these equations. Let's translate these from exponentials to log, and those from log to exponential. And we'll just see what we think of the result. Pi cubed equals m. What does that become if you put it in logarithmic form?
So I guess the first question, what's the base? Pi. Because pi is the base in that exponent.
Log base pi. What's the thing in the parentheses? M equals 3, the thing in the exponent on the other side. E to the x equals 9, what does that become? Yeah. Or you could have equally well written log base e of 9 equal to x. Because log base e is the natural logarithm. Both of those mean the same. Could you do the reverse on the other side? Yeah, maybe I'll pause for a moment. Let you do that. All right, log base pi of 3 equals m. What does that become in exponential form?
Pi to the power of n equals 3.
Pi to the mth equals 3. Natural log of x equals 9. E to the 9 equals x. All right, any questions about those? All right, well, I'm going to ask you a question about these. So let's suppose you saw these equations. Each of them have something that's obviously a variable. It's the thing that's a letter. If I asked you to solve these equations, when you did this, let's just answer the question, did you make your life better or worse if you wanted to solve for that variable? If I gave you that equation and asked you to solve for m, did you make your life better or worse? Worse. You'd already solved for m. Better or worse? Better. You have now solved for x. Sometimes writing things in logarithmic form lets you solve for the variable you want. And right, like, it's obvious when to do that. When the unknown is in the exponent, you get it out of the exponent by putting it in log form. Other way too. If someone tells you the log base pi of 3 is equal to m, and you write down pi to the m is equal to 3, have you made your life better or worse? Worse. You already knew what m was. For some value of no, right? You have to convince yourself that you know what log base pi of 3 is. ln of x equals 9. Yeah, you've made it better. You now know exactly what x is. It's e to the 9th. Another powerful thing you can do with this is a lot of times you can't compute logs directly. We'll talk about how to ask a calculator how to compute the things. You can compute some things directly by using this idea, though. Let's try to directly compute log base 4 of the power 32. And here's how I'll do it. First, I'll give it a name. I don't know what it is. I'll call it star for now.
Maybe you can use a better variable. Doesn't matter what the variable name is, though. We'll call it star. That look like an equation that's in logarithmic form? Can we put it in exponential form?
Yeah. This becomes, what's the base? To the power equals?
So that's now an exponential equation. On the one hand, maybe you're a little bit sad because this is exactly when you just told me that life has become worse. Do all those exponentials have the same base, though? Kind of. What's the common base? 2.
So on the left-hand side, really I see 2 squared to the star is equal to, I guess 32 is also a power of 2 then?
Yes.
What power of 2 is it? 2 to the 5th. Oh, does that look like an equation that we maybe did like last time? Yeah, what was the idea we used to solve that? Yeah, once we can get everything to just have the same base, we can cancel the bases. This doesn't quite have the same base as the other side yet, but what's 2 to the power star? What happens when you exponentiate twice? Yeah, you multiply the exponents. 2 to the 2 star equals 2 to the 5th. Oh, neat, and powers of 2 are injective. 2 to the star 2 times star equals 5. Star equals 5 over 2. So that means the log base 4 of 32 is 5 halves. And you know what? Let's go ahead and check that just in order to demonstrate that you can double check these things. So, let's ask, what is the log base 2 of 32? Log base 4 of 32. Oh, really? Log base 4 of 32 is 5 halves, or 2.5. Folks feel pretty good? Nice. Let's play the same game. Let's try to compute the log base 10 of 10. And this one will be a similar problem, but like way easier. And we'll see a general fact as a consequence. So let's give that a name. Let's call it star. And what does this now become? It means, well, I need to figure out 10 to what power is equal to 10.
And that's like easy to answer, right? What power of 10 is 10? The fourth power of 10 is equal to 10.
So that means star equals 1. Log base 10 of 10 is just equal to 1. In fact, if I give you any base b and ask you for the log base b of b, what do you think it's going to be? 1. Log base thing of that same thing is 1. Because what power do you raise b to get b back? 1. All right, cool.
So let's use this to do a quick check. I told you that some calculators will walk in base 10 naturally, some will not. Let's check a few calculators and use this as the check to use. So if you've got your own, take it out and ask it, what is the log base 10? What does your calculator say? Nope, log of the 10. Folks whose calculator said 1? Cool. Your calculator walks naturally in base 10. When you just ask it for the log, it will be walking with the log base 10. Let's see what a few others do.
Well, maybe I'll go through like the whole list. The Google calculator appears to walk in base 10. Wolfram does it seem to walk in base 10?
No. Wolfram's a tool that's made by a mathematician for mathematicians. It walks in base E because that's the most natural base.
And I think it even gives you the option, assuming log is the natural logarithm, you can tell it to use base 10 if you want. What other online calculators do people like? Desmos. Happily I have that pulled up. Let's figure out what it thinks when you just type log. So there's the graph of log of x, apparently. It certainly looks like the inverse of an exponential. How could I decide which one? How could I figure out what base it's using? Yeah, let's figure out what it looks like over x equals 10. And in order to not do the thing where you like drag along, I'll just draw the line at x equals 10 so that it will give me the point of intersection. Does it appear to be walking base 10? Mm-hmm. Nice. Groovy. As we progress, we will talk about how to deal with the fact that maybe your calculator only seems to walk in the 1 for odd base. We'll talk about how you translate between. Folks feel good? Nice. All right, let's use logarithms to do some stuff. There's an equation that we couldn't solve last time. 5 to the x is equal to 7. Let's solve that for x. And I'll even propose a fourth step. That's something in exponential form. The unknown is in the exponent. If I translate it to log form, suddenly the unknown will be on its own. Let's see that in practice. Let's rewrite that in log form. What do you get? What's the base of the exponent? 5. So log base 5 will be what you get when you write it in log form. What will be the thing in the parentheses? 7. The thing on the other side of the equal sign becomes the thing in the parentheses. And then the thing in the exponent is now solved for. So x is equal to the log base 5 of 7. We now know what x is. Suppose you wanted to know what value that is. You want to use your calculator or something. And on the one hand, some tools will just let you walk in multiple bases. Log base 5 of 7 is apparently around 1.2. How many people's handheld calculator, as far as they know, only seems to have the 1 or 2 buttons that say logarithm? An ln button and a log button. Yeah. It might have a way of entering multiple bases. The truth is you don't really need one. So this is a rule that we will establish and explain why it's true next time. But just for the sake of computational tools, whenever you see a logarithm that's walking with a base that you don't want to use, you can walk with respect to any base you want. Divide by the logarithm of the thing in the base, and the thing in the parentheses will become the log in the numerator. Let's just see that that's true. Log of 7, divide by log of 5. And I've separated them by commas, so it should just give me that thing twice. Do those two seem to be equal? Mm-hmm. Nice. And this was using Wolfram Alpha, so that's walking with natural log when I don't specify a base. Those of you who just did this using your calculator, which will walk base 10 probably, get the same thing? Yeah. So here's another magic secret. When you do this change of base formula, it doesn't matter what the base on this side is, as long as it's the same base for both of those logs. That feel pretty good? Cool. All right, let's carry on and combine this with other ideas. Let's solve some more equations. Let's solve this. 3 to the power x, then square that, is equal to 8. And we have this new fancy tool of rewriting in log form. And that's a good idea once
the unknown is the thing in the exponent. Is the unknown in like the exponent right now? No, it's not even clear what you mean by the exponent. There are like two of them. There's a 2 and there's an x. So I think it's a bad idea right now to just rewrite in log form because it's not even so clear what that would mean. What would you want to do to this? What seems like an idea? I think there are 2 sensible ones. Yeah, here's one idea. Look at the stuff on the side that has the unknown. There's only one unknown. So you can just try to undo things one at a time. Eventually you'll get down to what you want. So let's undo that squaring boss.
Here's like strategy 1. Square root both sides to get rid of the square. 3 to the x is equal to the square root of 8. Should we simplify that to 2 root 2 or leave it as the square root of 8? Leave it as root 8? 2 root 2. All right, I'll leave it as root 8. Nice.
So let's look at what we have now. Now does it seem more useful to rewrite in log form? Yeah. In fact, it looks super useful. Bx is the only thing in the exponent.
X equals log base 3 of the square root of 8. And we'll get a decimal approximation in a little bit. There's one strategy.
And that's like, you're walking automatically. You say, it looks like I can just undo everything. Oh, in fact, did I lose anything? Is there any problem with what I did? I was sloppy at one step. When you undo a square with the square root, what should you introduce?
There should be a plus or minus sign. So let's introduce that plus or minus sign. And then maybe think about why it doesn't matter.
So that's really like 2 equations now, right? It's 3 to the x equals 8 or 3 to the x equals negative 8. Nope, square root of 8. Is the power of 3 ever negative? So I don't need to worry about the negative case anyway.
Three to the x can't be negative. So I don't need to worry about the negative root 8 case anyway. Cool. Seem all right so far?
And we could get a decimal approximation, but like I said,
We'll do that in a bit once we address the other strategy. So take a look at that starting equation.
what's something else that you could do to that? Like maybe simplify before you try to solve. Yeah. Yeah, I see 3 to the x to the power 2. Nope, 3 to the 2 to the power x. That's the same thing as 3 to the 2x. Oh, cool. Is that something that's now in exponential form? All the unknowns in the exponent?
Let's rewrite that in logarithmic form. What's the base? Log base 3. The base is still the base of is equal to the thing in the exponent. Does that look easy to solve for x? What do you need to do to get that x on its own? Divide everything by 2. X is 1/2 log base 3 of 8. So we solved this 2 different ways.
Do those 2 answers look different? Yeah, I mean, kind of. So really what I'm hinting at is there are like algebraic rules that logs follow, and we just uncovered one thing. Those 2 things better be the exact same. Let's test if they're the exact same. Let's just get decimal approximations for each of them. So, I'll pull this up on my end. How many people have already gotten decimal approximations for the first of those while I was rambling? What'd you get?
Cool. And it's approximate. Next one. what did you, so, yeah, maybe I'll just pause and let you practice using the calculator if you got one. Yeah. What'd you get? I hear the same thing. That's good. Nice. All right. So here's the main point that I want to bring across with those examples. If you can take the log of both sides, then there are new equations that you can solve. And some of those equations, I didn't give you any reason to care about those equations. They're just things I wrote down. Let's write down something that might be closer to something that you care about. Let's go back to this population growth example. You've got a population of tribbles above the enterprise. Its population is modeled by the function 2 to the power t. The life support systems will be overwhelmed once the population hits 30,000 tribbles. How long does the crew have to solve that problem? So, right, like obviously this is like a mildly bullshit example, but you could imagine adjusting this to be a population growing that you do care about. It'd be modeled by a different exponential function, but you'd have one. Let's write down an equation and solve this. Let's write down an equation that models this problem. We want to know when the life support systems will be overwhelmed. When will the life support systems be overwhelmed? How could you write this as an equation to solve? Yeah, okay, so you've jumped right to the answer instead of like. Yeah, 2 to the t, there's the population. You want to know when that is 30,000. That's when the support systems will be overwhelmed? Oh, is that just an equation in exponential form that you can just put in log form? Nice. And I guess if you want a decimal approximation, well, you can just like get one. So it will happen at time log base 2 of 40,000, which is I'm going to continue using this notation just to reinforce it. At about 14.9 hours. That agree with other people's computation? Yeah. So, again, there are like a few things to point out. 40,000 is like a big number. You plug it into log and you get something that's like pretty minuscule by comparison. Like 15 hours. Logs grow, they keep on growing as you plug in bigger numbers, log keeps going up. But it slows down by a lot. It gets real slow. You know. So, I think what I want to do here is I want to sketch the graph of various logs with different bases. And to do that, I guess we have to sketch the graph of the various exponentials. So let's try to do that. What does the graph of b to the x look like if b is bigger than 1? So it has this, if you take something like 5 and raise it to a positive power, it keeps getting bigger, it grows real fast. If you start plugging in negative powers, that means you're like dividing by 5 a bunch of times. So you should have this nice like horizontal asymptote as t goes to, as the input goes to minus infinity. Oh, and I guess I've drawn a dot at the y-intercept. Let's label the y-intercept. What's b to the power of 0? 1. So there's this point at 0, 1 right there. What if I plug in a number that's less than 1? So like a fifth. If you keep multiplying by a fifth over and over and over again, it gets smaller instead of bigger.
So as x gets big, it will go down.
And if you divide by 1/5 a bunch of times, that's the same as multiplying by 5 a bunch of times. That'll get big on the other side. So there's the graph of b to the x when 0 is less than b is less than 1. I guess the remaining case is, what does the graph of b to the x look like? Why don't I have a green pen in that pen case? I have green pens. b to the 1. What does b to the 1 look like? Nope, 1 to the power b. 1 to the x. What's 1 to the x? Straight line. At height? 1, I guess? And that's what any exponential looks like. Any exponential function looks like one of those. Let's graph their inverse functions. If the base is bigger than 1, then these correspond to very negative x values, very small y values. Over here, they'll correspond to very small x values and very negative y values. That sounds like a vertical asymptote. Goes to the point 1, 0. Goes like that. It looks roughly like log base 2. The pink graph is basically the same as the blue graph reflected over the y-axis. Flip the roll of x and y, now you'll be flipping over the x-axis. So there's the case that 0 is less than b, less than 1. What if I do the same thing to this green graph? What does it become? A vertical line. Is anything wrong with that? Yeah. I think people said the word vertical line test. It fails like really badly at x equals 1. All right, so let's talk about valid bases. You can only talk about log base b of x in the following circumstance. 0 had better be bigger than b. 0 had better be less than b. Otherwise, like you can't even talk about the exponential that you're trying to invert. Negative 5 to the x doesn't make sense. And it better not be 1 because then log base 1 of x, like you're inverting a not one-to-one function. Oh, yeah, sorry. Log base b only makes sense when b is positive and is not equal to 1. Let's read off some domains and ranges. So check out either the pink graph or the blue graph. What are the domains of those functions? Let's read them off. Are negative numbers in the domain? Nope. Is 0 in the domain? Are positive numbers in the domain? Are any positive numbers not in the domain? Cool. So I think it's just 0 to infinity. Never include infinity. Should I include 0? No, because you specifically told me that 0 isn't in the domain. What about the range? What are the ranges of those functions? Negative infinity to infinity. All real numbers if you like that better. Cool. Feel pretty good? So we have some properties of these functions. Oh, yeah. So let's also, it's unfortunate this is on the next page. You might have to flip back to the previous page. Well, I guess I'll flip back to the previous page. X-intercept, vertical asymptote, horizontal asymptote. Looking at these graphs, tell me about their x-intercept. at x equals 1, at 1, 0, if you want to be super pedantic. Tell me about their vortical asymptotes. At x equals 0, which you wouldn't specify that as a point because it's supposed to be a line. So the vortical asymptote is at x equals 0. Any horizontal asymptotes? No, it will keep growing. It looks like it's flattening out, but it will just keep on increasing forever. It will exceed any threshold that you set for it. So no horizontal asymptotes. Feel pretty good? Nice. So we can read awesome things from the graph. And so x-intercept at 1, 0, vortical asymptote at x equal to 1. It has a horizontal asymptote at, nope. I guess if you want to so there's I know very little about the Drawman language, but in talking to people who are wanting a little bit of Drawman, there are 3 answers you can pose to a yes or no question. One is yes, one is no, and one is I disagree with the premise of this question. And there's a wad for that. I disagree with the premise of that question. It's a question that you can't fill in that blank. All right, so I have 8 minutes left. My goal for the remaining 8 minutes is fairly explicit. I want to talk about finding domains of things involving logs. And I want to talk about graphing by transformations. Both of those I think are pretty attainable in the time. In order to compute the domain of something involving a log, let's just remember this. Domain of log base b of x. Flip back to the previous page if you need. What things are you allowed to plug in? What's the domain of that? 0 to infinity. So that means the thing inside of the log needs to be strictly positive. So it's kind of like with square roots, except it's a strictly greater than instead of a greater than or equal to. You can find domains of things involving logs the same way as you would the domains of things involving square roots. Let's find the domain of this thing. Let's find the domain of the log base 2 of 3x minus 4. So the idea is the thing inside of those parentheses has to be strictly positive. So what inequality should I write down if I want to find this domain? Well, whatever it is that's inside of the parentheses has to be bigger than 0. This domain is given by 3x minus 4 strictly bigger than 0. Oh, is that an easy inequality to solve? Yeah, okay, solve it. That sounds right. People feel confident? Let's hear someone confident enough to say the answer and project. I think what you said was right. X bigger than 4 over 3? All right. So you'll notice that I did nothing to solve that. I just waited for you to tell me. Should I do any of the work? Okay, cool. Maybe I'll just conclude with, let's put that in interval notation. I guess I don't specify in the question how I want the answer formatted. But what way? Cool. With the 5 minutes I have left on the clock, I think I would like to talk through one of those remaining 3. And I'll let you all decide which one. And then think about graphing by transformations. If they're A, B, and C, how many people would like to talk about A? B. C. I think the B's have it. We can
talk about, see if there is time.
So, there's a thing whose domain I would like to find. In order to find that domain, I need to write down an inequality that I solve that inequality. So let's start by just writing down that inequality. What inequality should I write down? Yeah. Not just 1 minus x. That whole thing needs to be bigger than 0. Because it could be that, like, when x is negative a billion, I think the top is negative and the bottom is positive. Okay, so that one is bad. I think there will be some inputs other than just that. Or maybe not. Let's write down the whole thing and see what happens. 1 plus x over 1 minus x is bigger than 0. That looks like an inequality involving rational functions. So we can't just do what you might have done before and like solve the inequality directly. There are like 2 steps that I'll want to follow. Whenever you see a complicated inequality, what should your first step be? Yeah, do equality instead. This is a rational function, so I'll also have to worry about vertical asymptotes. So x plus 1 over 1 minus x equals 0. Oh, does that look like it's super easy to solve? Yeah, the only way a fraction can be 0 is if the numerator is 0. Numerator is 0 when x is negative 1. Vertical asymptote. Where does that thing have a vertical asymptote? I hear a 1. And now we will play the check some sample points game. Negative 1, 1. What's an input to the left of negative 1? Negative 2. Let's plug negative 2 into that, see what we get. 1 minus negative 2 over 1 plus, nope. 1 plus negative 2 is in the numerator. 1 minus negative 2 is in the denominator. Is that positive or negative? Is it? 1 plus negative 2 would be negative 1. 1 minus negative 2 would be 3. I think it's negative, unless I'm screwing up. Okay, excellent. So that means that anything to the left of negative 1 is not in the domain. Give me a sample value between negative 1 and 1. 0. 0 is an easy number to plug in. Plug 0 into that. What do you get? Yes. Good. Okay. I was getting not 1, but you're right. So x equals 0 goes to this thing being equal to 1. Should those numbers be included or excluded? Numbers bigger than 1, do you think they'll be included or excluded? Excluded. How many people have actually already checked a sample point? Cool. Can you confirm? Excellent. Those numbers will be excluded. And so it looks like the domain is negative 1 to 1. Include the endpoints or exclude? Well, let's see. 1 is a vertical asymptote, so it's definitely excluded. You divide by 0. Negative 1 corresponds to the whole thing being equal to 0. So should I include or exclude? Also exclude? Because I want strict inequality anyway. Cool. All right. So I guess I'm not fitting in the graphing by transformation example. That's somewhat tragic because the problem I'm going to have you do with the canvas homework will be a graphing by transformation. But I don't know. You know how to graph by transformation, right? If you want to graph that, well, I guess you go left 1, then down 1, then you divide the x values by 2. Did I do something wrong? Oh, yeah. You always do the opposite of what you expect for things inside the parentheses. So, if it looks like you double all the x values, you really have it. And remember, you can check it by like grabbing. Yeah, see you. Oh. Stop recording.